Deep in rural Java, local artisans process raw cassava root under the open sun to produce a traditional noodle known as Mie Lethek. The nutritional profile of this food is highly uniform. It consists of roughly 89% carbohydrates, with almost zero protein or fiber enrichment. This line graph shows simulated gastrointestinal digestion of the noodle over a 240-minute window. Based on its macronutrient profile, we expect a rapid spike in glucose. Instead, the release curve flattens, resulting in a moderate estimated glycemic index of roughly 69. A food composed of nearly 90% starch that fails to trigger a high glucose spike suggests the physical manufacturing process is altering the digestibility of the raw ingredients. Artisanal food production functions as a systematic biochemical engineering pipeline. Mapping how this process manipulates carbohydrates requires three analytical layers: thermodynamics, microstructure, and biotechnology. We applied differential scanning calorimetry to quantify thermal stability. We use scanning electron microscopy to analyze physical architectural breakdown, and Fourier Transform Infrared spectroscopy to track shifts in chemical bonds. The raw material entering this pipeline is goplek, sun-dried cassava root. Modern industrial carbohydrate processing relies on high-pressure extrusion and refined inputs. This method uses indigenous techniques to achieve its functional outcome. By treating traditional Javanese kitchens as bioprocessing environments, we can identify specific methods for producing functional foods from simple raw materials. The process begins by hydrating the dried goplek and exposing it to ambient air for 48 to 72 hours. Unlike industrial processes using lab-grown cultures, this relies on spontaneous aerobic fermentation. Environmental microbes colonize the cassava, secreting enzymes that degrade the raw carbohydrate structures. This initial enzymatic breakdown chimes the starch, physically modifying its macrostructures to respond more effectively to downstream thermal processing. After fermentation, the dough is extracted, washed, and combined with pure tapioca flour. Blending the degraded goplek with pristine tapioca creates a heterogeneous starch system with a wide range of molecular weights. This configuration influences the final digestive behavior. The combination of fermentation and blended flours creates a matrix where over 63% of the starch is classified as slowly digestible. The reliance on ambient fermentation acts as a necessary biological primer, which contributes to the formation of enzyme-resistant starch later in the pipeline. The dough then enters the thermal stage, undergoing repeated steaming cycles inside wood-fired ovens. When starch is exposed to heat and moisture, it undergoes gelatinization, a process where crystalline structures are disrupted as they absorb water. This thermogram plots the differential scanning calorimetry data from the final noodle. It maps heat flow against temperature to show the specific reaction of the starch. The onset temperature is approximately 57 degrees Celsius. At this point, the starch matrix begins the swelling process. The process concludes at 121 degrees. This broad range indicates a highly heterogeneous population of starch granules with varying levels of resilience. The total enthalpy value, the energy required to disrupt the crystalline bonds, is nearly 418 joules per gram. This confirms that many internal crystalline bonds remain intact. The fluctuating heat levels of a traditional wood-fired oven drive this specific thermal profile. The result of this process is partial gelatinization. The starch granule is heated enough to become workable, but it is not completely melted or collapsed. In contrast, most instant noodles are intentionally and completely gelatinized to ensure rapid rehydration by the consumer. By remaining partially gelatinized, the physical structure of the granule continues to restrict digestive enzymes from accessing the carbohydrate chains. Traditional wood fire steaming cooks the starch while leaving a significant portion of its physical resistance to enzymatic hydrolysis. After the steaming process is complete, the noodles are rested overnight and carefully spread across bamboo trays for ambient sun drying. As the starch cools and loses moisture, it undergoes retrogradation. The disorganized starch chains realign themselves into ordered semi-crystalline formations. The slow evaporation rate of solar drying provides the specific time and temperature profile required for this realignment to occur. Javanese sun drying functions as a thermodynamic curing process, building a crystalline defense that slows the rate of human digestion. Between the thermal stages, artisans apply intense mechanical force using a 1-ton stone cylinder to crush the dough. This shear stress serves to mechanically homogenize the partially gelatinized matrix. This micrograph shows the resulting surface architecture, a dense physical matrix with spherical starch granules firmly embedded inside. The visible pores are the structural voids left behind as water slowly evaporated during the sun-drying stage. An intermediate soaking step removes surface mucilage, further defining the boundaries of the noodle strand. Fourier Transform Infrared spectroscopy allows us to track denatured proteins in this matrix by examining the amide I region between 1600 and 1700 inverse centimeters. This specific peak identifies the presence of beta sheet structures. Deconvoluting the data reveals that beta sheets make up roughly 50% of the protein structure, far outweighing alpha helices. The heat from the processing has denatured the trace proteins, forcing them to cross-link via tight hydrogen bonds. This results in a tightly aggregated protein net. This net physically encases and wraps the retrograded starch granules. Heavy stone milling combined with specific heat cycles constructs an ordered microarchitecture that is difficult for digestive enzymes to penetrate. The biological and structural data reveals a clear model, a beta sheet protein net surrounding a partially gelatinized core and retrograded starch crystals. During digestion, alpha amylase enzymes attempt to penetrate this matrix, but physically fail to rapidly bypass the dense beta sheet structures and semicrystalline starch walls. This slow structural breakdown maps directly to the plateauing glucose release curve shown earlier. The moderate glycemic response of Mie Lethek is a direct outcome of the specific processing pipeline used to create it. The health properties of this heritage food are built through processing methods that manipulate thermodynamic and biological laws. Traditional cultural practices often reflect complex biophysical principles. These methods use raw materials and sunlight to produce a noodle that is both structurally resilient and nutritionally distinct. This pre-industrial pipeline provides a blueprint for creating low glycemic foods without relying on synthetic additives or highly refined grains. By analyzing indigenous culinary methods, we identify specific bioengineering models capable of addressing dietary needs